Okay, so what's kind of interesting is, oh, sorry, that square root doesn't look very good. Let me just fix that. The square root is just the number up front, okay? The AK is not under the square root. So take a look at this, okay? The 2 pi cubed, well, that's just a number, it's just a constant. So this is related to my conventions of wanting to get the 2 pi's simple in the final Feynman rules. But we've got a 2 omega k, so that's an energy dependent factor. And it in fact turns out that to pass from Lorentz invariant oscillators to the usual oscillators, you do that by multiplying by an energy dependent factor. So I'd like to explain that now, okay? So I don't only need to know how alpha transforms, I also need to know how alpha dagger transforms, but I can get that by daggering the boxed equation. So if I dagger the boxed equation, well, I will get alpha k dagger is equal to, so the square root factor is real, so complex conjugate of it remains the same. So I'll still have 2 pi cubed. I will still have 2 omega k. And then AK daggered is just AK dagger. Good. Okay, so now let's really check and see if these oscillators are Lorentz invariant or not. And the way to check that is, let's calculate the commutator, okay? So let's take alpha p, comma, alpha k dagger. And these numerical factors multiply by each other. So the square root of 2 pi cubed from alpha k will multiply by the square root of 2 pi cubed from the alpha k dagger, and we'll just get a factor of 2 pi cubed. Now the omegas are not the same, so I better keep them both. So from the alpha p, we'll have a 2 omega p, and from the alpha k, we'll have a 2 omega k. And then we will have AP, comma, AK dagger. Now that commutator, you know, okay, it is just the Dirac delta function, the Dirac delta distribution. So we will have a delta of P minus K. Now remember, the Dirac delta is only non-zero when P is equal to K. So it's perfectly valid to evaluate whatever multiplies the delta function at K is equal to P. And if we do that, then we get 2 pi cubed. Inside the square root, you get 2 omega p times 2 omega p. So the square root of that is just 2 omega p. And then we've got a delta of P minus K. And the good news here is, if you remember, 2 omega p times the delta function is Lorentz invariant. Great. So these commutation relations are what define the oscillators. And now we find that indeed these are Lorentz invariant. So all inertial observers will agree on what the oscillators are. The last two commutation relations are pretty trivial to work out, but let's just do it. So again, we've got the factors, 2 pi cubed, the square root of 2 omega p, 2 omega k, and then we've got the commutator between AP and AK. And of course, that commutator vanishes, so this is just 0. And in exactly the same way, I invite you to check that alpha p dagger, alpha k dagger is also 0. Good. So here are the 5 axioms for our scalar field. Axioms A1 and A2 must be obeyed by any field that we consider. A1 says space-like separated fields commute, and that's to be consistent with relativistic causality. A2 tells us phi dagger is equal to phi, and this is the fact that in quantum mechanics, operators are Hermitian, observables are Hermitian operators, and it ensures that the eigenvalues of the field phi will be real, so that when we measure the field, we're going to get a real value. Okay, so this, let's just make a comment that this first section over here should be true for any field, okay? So we never want to mess around with that. This is a good set of axioms to have. The second set of axioms, well, this tells us how our field transforms under translations, that's A3, and under Lorentz transformations, that's A4. So this is what we mean by a scalar field. And then finally, this last axiom, A5, this is where we said we build the field out of harmonic oscillator creation annihilation operators. And this is where we put in the fact that we are dealing with a free field. Now, in fact, A5 is not on the same footing as the other axioms. A5 was guessed. So now we're going to try to solve these 5 axioms. And if we find that there's no solution, the axiom that we're going to change, or the assumption that we've made that we're going to change, is A5. And we'll maybe have to mess around with it. Actually, it'll turn out that these 5 axioms will have a solution and we'll get a quantum field. The good thing about getting a quantum field is that we can then start to study it, and we can start to explore what properties does it have, what can we learn from it. Okay, so that'll be our first example of a quantum field, and we'll want to study this in detail. Okay, so let's start off. And I'm going to say that this is my field. Okay, so this is the field that we're going to study. Okay, by doing this, by saying that this is my field, well, I have already satisfied axiom A5. Okay, so I'm going to start ticking off the axioms as we satisfy them. Axiom A5 we've satisfied just by taking this as the mode expansion. Good. Now, next I would like to satisfy axiom A2. So phi dagger must be equal to phi. Okay, so let's see what that means. So let's calculate phi dagger. So phi dagger of x is equal to, well, the measure is real, so nothing is going to change there. We'll get integral d3k over 2 omega k, 2 pi cubed. Good. That's the measure. And then this function f will be complex conjugated. So we'll get fk of x. By the way, let me maybe just stress, the k and the x appearing here are 4 vectors, as I've written above. So k mu is omega k and spatial k, and x mu is t comma x. Good. Okay, so taking the dagger, we'll complex conjugate fk of x. So I get fk star of x. So the star is complex conjugation. Alpha k will become alpha k dagger plus the dagger will complex conjugate gk of x. And alpha k dagger, daggered, is just alpha k. And I would like this to be equal to phi of x. Well, we can see phi of x in the line above, okay? And what you can see is, here is the alpha k term, and there is here's the alpha k dagger term, here is the alpha k dagger term. If we want phi to be equal to phi dagger, those coefficients must be equal. So the first thing that we learn is that gk of x must be equal to fk complex conjugate of x. Next, here is the coefficient of alpha k. Sorry, here is the coefficient of alpha k, and here is the coefficient of alpha k. So if we want phi to be equal to phi dagger, those coefficients must be equal, and we learn that fk of x must be equal to gk complex conjugate of x. And of course, these two equations over here are not independent. They imply each other by taking a complex conjugation. So what we can do to satisfy the second axiom, instead of taking gk as an independent function, let's remove gk and let's replace it by fk star of x. And then we are guaranteed that our field is Hermitian. So let me just clean this here now. We don't need this anymore. And what have we done? Our field is now Hermitian. Very good. Okay, so let's go back to the pen, red. So we've satisfied A5 and we've satisfied A2. We'll continue in a moment.